Cool. Okay, so hello everyone. Thank you for hanging around for the last session today. I think we've had a really great overview of some of the simulations and the theory behind black holes and tidal disruption events, and then the visible observations, so the optical. And so now I'm going to kind of look into the radio emission that we see from these sort of things. And so when we're thinking about radio emission, it's quite different to optical and X-ray and UV emission in that the radio emission often tracks the ejected material. So X-rays and optical come from the material that's accreted or that's being swallowed by the black hole. But the radio emission actually comes from much further out, and it's from material that's moving away from the black hole. And so my favorite thing to say is that black holes are messy eaters. So I think when I was a kid, I used to think that black holes were terrifying. I thought that they just sucked everything in, and they were these really like big sucking machines. But now I know that that's actually not really the case. Like, yes, they do accrete material, and material does go into them through accretion, but they're really messy eaters, and accretion is quite an inefficient process. And so that means that black holes actually drive some really powerful outflows, and then these illuminate in the radio, and that's how we are able to track black holes in that way. So the first type of outflows I think it's important to mention are these things called AGN and quasars. So these are active galactic nuclei. Quasars are sometimes called QSOs because back in the day when they were first detected, when we first had radio telescopes taking observations of the night sky, they saw these really compact, really bright radio sources. And so they called them radio stars because they thought that they looked a lot like a star. It was a point source in the night sky. They were really bright. The logical explanation was that they were stars. However, they were able to go and look at them in the optical. A few sources they were able to look at in the optical, and they saw some emission lines, and they were able to then get a redshift for these things. And it turned out that these objects were millions or billions of light years away. And yet they were very point-like, and they were emitting a lot of radio emission. And because they were so far away, but that bright, that meant that the luminosities of these things were huge. And it kind of didn't even make sense because this was before black holes were technically observed. They were still a theoretical concept. And so they called them quasi-stellar objects, QSOs, because they looked like stars, but they weren't quite stars. Of course, now we know that these are active galactic nuclei. And so these are supermassive black holes in the center of galaxies that are accreting a lot of gas. So if you think about a galaxy at its most basic level, there's a lot of gas hanging around in most galaxies. And so there's a huge reservoir of gas that the supermassive black hole can accrete. And in some galaxies where there's a lot of gas around, the black hole will accrete so much that it will power these massive outflows. So this is a very nice galaxy. This is called Centaurus A. And this is what this galaxy looks like in the optical. So this is visible light. Quite a gorgeous galaxy. You can see a bit of structure. It looks a bit dusty, all those sort of things. If we then look at it in the radio, this is what we see. So you can see it looks very different. And it's got these two kind of lobes of these are jets, actually, that have been launched by this supermassive black hole right here in the center. And now, just looking at it in the radio, it's kind of hard to get an understanding of the scale of these jets. So here, I didn't plot this, but someone has overplotted the radio emission over the optical image. And so what is clear is that the radio outflows here are way bigger than the entire galaxy. So these are huge jets, and we see plenty of AGN like these. We see small AGN, we see big AGN. But this kind of just gives you an idea of the type of scale of outflows that black holes can drive. So it's pretty impressive. So yes, black holes can drive extremely powerful outflows at the centers of galaxies. And in fact, now we're lucky enough to have plenty of radio telescopes that are looking at the sky all the time. And we see some really gorgeous looking AGN. Every radio image I take of the sky, it's nice to have a look. Because there's always background AGN that look like this. Yes, we have a question.
How long do they last?
Yeah, that's a good question. And we're not entirely certain because These things evolve on much, much longer timescales than we've been looking at the night sky. But our best guess is that they're actually quite short-lived in that they last maybe tens of millions of years. And so galaxies might go through this phase where they've got this big gas reservoir, the black hole will start accreting, will launch these powerful jets. And when the gas runs out, there's only a limited amount of gas in a galaxy. It will switch off the active part of its life cycle, and it will kind of become a remnant. Yeah?
How long would you be able to see that there was a...
Yeah, that we're also not too sure. It's something that there are some galaxies that have hints of kind of an indication that AGN activity has happened in the past. And I'm not a galaxy evolution person, but I know there are plenty of people working in the field of galaxy evolution where they think that the feedback mechanism between these huge outflows can actually affect the evolution of the galaxy. So if the black hole is kind of eating all of the gas that's in the galaxy, that means there's less gas available to form new stars. And so they actually think that AGN can have quite a strong role in the feedback to the life cycle of the galaxy and can actually, they call it quench the star formation. So it can mean that the galaxy no longer forms as many stars. But this is very much an active area of research still. So they power these huge jets. They look really nice. They all have different shapes. There's no one exactly the same. Some of them we see them face on, some of them we see side on, and they all look quite different. So this is a diagram of what we think an AGN looks like. So you have the black hole right here in the center. We think that sometimes when we don't see the jet, so the other thing about jets is that they're relatively narrow, and so you have to actually be pretty lucky to see one because it has to be oriented towards you or within an angle that it's actually visible to you. So if we were looking at this from the side bays, all we would see was this obscuring torus, and we might not even see the jets. So the viewing angle of these things is actually quite important, and of course space is 3D, and so we see AGN in all sorts of different angles. And so we think that the jet will interact with the stuff that's in the galaxy, the medium, and this drives the radio emission that we see. But not only do supermassive black holes drive outflows, but so do stellar mass black holes. And I think today we've had a bit of a chat about the two different kinds. We've really mainly focused on supermassive black holes because this is a tidal disruption event conference, and tidal disruption events primarily occur, they're primarily visible around supermassive black holes because they are kind of much more luminous. But stellar mass black holes also exist, and this is what we call an X-ray binary. So a lot of stars in the night sky are in binary systems, or even multiple systems. There might be 3 or more stars. If a very massive star is born with a lower mass star, the massive star will evolve very quickly and it'll die and become a black hole, while the other star will just kind of hang around because low mass stars live a lot longer than massive stars, and massive stars are the ones that become black holes. And so you can actually end up with a system in which you have a black hole in a binary system with a regular star. Now this is one of the ways that we think these things form. There are other theories that some black hole X-ray binaries are formed by the black hole capturing a wandering star. But yeah, we can talk about that if you're interested. So yeah, we have these things called X-ray binaries. You have a black hole in a binary system orbiting, or with a regular star that is orbiting it. And occasionally these orbits can be so close that the black hole will actually pull gas from the regular star slowly over millions or even billions of years into an accretion disk around the black hole. And this drives very bright X-ray emission, because as soon as we have accretion occurring, we tend to get very high energy radiation. So we see X-rays from these systems, and also jets. So also when there's an accretion disk and we have magnetic fields, we get jets. And so we see jets from many of the accreting stellar mass black holes in our galaxy. It actually gives us quite a nice way to view jets from black holes that aren't these huge AGN jets because they are within our galaxy, so they're relatively nearby. Now, through popular demand, I think I just added these slides during the break to my talk because I think people will probably want to see this. Now, I usually show this in my outreach talks. So this is a photo of our galaxy, and I say it's a photo because this is actually a map of our galaxy that was taken by the Gaia space satellite. So every little speck you see is a star in our galaxy that has been observed by this telescope that's in space. It's an optical image. So you can see the galactic plane, you can see the large and small Magellanic clouds, which I'm lucky enough to see in Australia, which is where I'm from. And yeah, you can see towards the center of our galaxy, it's a lot more dense. That's kind of how the structure of galaxies are. And we think, look, we haven't counted them all, but we think there's about 100 billion stars in our galaxy. So that's a lot of stars. And what we know about stellar mass black holes is that they're formed when massive stars die. And we've been looking at stars for quite some time. We have some theoretical models about how stars form. So we can make a bit of a guess at how many massive stars would exist in our galaxy, or would have existed over the lifetime of our galaxy, that would be able to become black holes. So we've been looking since the, I want to say 70s, maybe 60s, for X-ray emission from stellar mass black holes in our galaxy. We've been listening with LIGO for gravitational wave events from merging black holes, but they're probably not mainly in our galaxy. And to date, we found 80 black holes in our galaxy. And every blue dot here is the location of one of those black holes. So if you were wondering about the stellar mass black holes in our galaxy, here's the answer. So 80 black holes seems like quite a lot. When I ask primary school kids how many black holes they think there are in our galaxy, they say 1 or maybe 2. And then when I tell them there's 80, they all are like amazed. They think that's so many black holes. And what's interesting is you can see that they're kind of more centrally concentrated towards the denser regions where there's more stars, more likelihood of massive stars that might become black holes. But there are some off in the halo and even a couple in the Magellanic clouds. So based on what we know about massive stars, how many there are, that there's 100 billion stars in our galaxy, we can take a guess at how many black holes there should be in our galaxy. And the answer is 10 to 100 million. Now, these green dots are not real observations, obviously. I haven't counted them. There's definitely not 100 million dots there. But this is just kind of to visualize that there are so many black holes in our galaxy wandering around that we will probably never see because they'll never interact with anything. And so this just really emphasizes the point that black holes are really, really hard to find. Or maybe there aren't that many black holes and what we know about physics is wrong. But I prefer the first option. As someone who works on black holes, I know how difficult they are to observe. I mean, by definition, you have an object that doesn't emit light. Light cannot escape the event horizon of a black hole. So the only way that we find black holes is when they happen to interact with something around them. And I mean, you might think that our galaxy looks pretty dense, there's a lot of stars, there's a lot of things happening, but there's actually a lot of empty space out there. And so the probability of the black hole that's not born in a binary system or not in one of these dense environments interacting with something else is actually quite low. So black holes are very hard to find. If you're wondering where they are in our galaxy, that's the answer to that question. Now, stellar mass black holes. So as I said, if a black hole happens to be in a binary system, it can accrete into an accretion disk around that black hole. And I wanted to show you this video because this is a really cool video of an observation of some jets from a stellar mass black hole. So this was observations taken by some researchers at my institute. Now these are the observations. So V404 Cygno, you can see this is actually what was observed in the radio. So they saw these blobs coming from the black hole and being ejected and moving out. And the time between those observations was hours to days. So these blobs were being ejected pretty quickly. And the interpretation of that, they knew it was a black hole, there was X-rays from this system as an accreting black hole. The interpretation was they were seeing the jets. And they were seeing the jets kind of processing, they say, so rotating. I don't really understand this bit, it's a bit wild. But the reason that the blobs were kind of moving and changing was because they were watching the jet come into out of view, and they were watching kind of clumps or clumpy bits of matter being ejected into into the jet. So I think that was a really nice observation because we actually can see in real time, in days to hours with stellar mass black holes, that launching process of the jets. I think that's probably the end of the video.
Primarily radio observations?
Yeah, so they were really high resolution radio observations taken. It's called VLBI. So basically, you can't just use one radio telescope. You need to use many spaced out across continents to get observations of that high resolution. And that's for black holes within our galaxy.
Would you mind playing the beginning scene again?
Yeah, sure. We can watch that again. Yeah, I think it went through it quite quickly, didn't it? So let's replay. So yeah, you can see this is about where the black hole is. Yeah, I have another plot that I'm about to show you that shows these observations in a non-video format that might make it a bit easier. So let's get to that. Okay, so this is the observations. Yeah?
So it's switching from an actual image to an animation?
Yes, yeah. It was that video was made with like outreach in mind. So they made it to accompany the paper so that people could kind of picture, rather than having this plot in the news article. It's a bit small for the general audience. But I thought I would show you this plot because this is actually what they saw. Well, you have a question over there?
So yeah, I had a question about that animation. So the animation was constructed from real-time data.
Yes.
I was curious, how long it's real-time? So the image reconstruction happens immediately, or?
Oh no, sorry, no. The animation was made after the observation. So okay, these are the observations, and so each of these images is the actual snapshots that they had. And you can see this one is on June 17, this one is June 22 at 12 o'clock, this one is June 22 at 1:20. So there's an hour and 20 minutes between these two observations, and you can see how much it's changed. And then they kept looking, an hour later, it's changed again, and then they looked again 4 days later, and it had completely changed, and then another day after that. Well, so they actually, the beauty of these observations is you can actually track these blobs, and they were traveling about 30% the speed of light. So they are traveling very fast, but not quite at the speed of light. But 30% is a significant fraction of that. So these types of systems, the accreting black holes, they do make gravitational waves. That's actually part of the reason the orbit evolves, because the companion star will come closer to the black hole over time, and then once the companion star loses too much mass, it'll actually start expanding again. But the gravitational wave signal from these types of X-ray binaries is very, very low. It's not, if you had two black holes orbiting each other, which is the in-spirals that they actually detect at the moment, the gravitational wave signal is much, much higher. So yes, they do make gravitational waves, but very, very low level. Yeah?
I have a question about these blobs. I mean, I'm imagining that the blobs are the radio emissions from like spiraling electrons.
Exactly, yeah, so these are the jets.
And so are these, I mean, when we say a blob is moving at 30% the speed of light, is it these electrons that are moving at 30% the speed of light?
Yeah.
Or is it the region of space that is being...
So it's the particles in the blobs in the jet that is all moving at that speed.
Okay.
Yeah.
Real quick, are the jets associated with the magnetic axis or with the rotational axis?
Yes, so the jets are actually associated with the magnetic axis. So the accretion, they're like in the opposite direction to the accretion disk, if that makes sense. So the accretion disk follows the rotational axis, and then the jets kind of come pretty much perpendicular to that, but not always perpendicular, which is kind of what the interesting result in this work was, that they actually discovered the jet was precessing. And so it was not always at 90 degrees to the accretion disk. It would like sometimes be here, and then it would sometimes be here, and yeah.
How was the determination of precession arrived at?
Yeah, so if you look at these images, so this X shows the axes of the jet in the first plane, and then if you look at the one over here, you can see it's changed. So they can kind of watch it wobbling around, which, yeah, these were really, really nice observations. So these were taken in 2015, and they're kind of just a really nice, demonstration of watching this jet activity in a stellar mass X-ray binary. Okay, so that's some observations of a jet. from a stellar mass X-ray binary. But I think the question that you all have, given some of the questions that we've had earlier today, is how do we actually launch these jets? So we have accretion, we have a black hole, there's a lot of gas, it's a high energy environment, but why are these, really fast and narrow things being kind of shot out from the black hole? And so the answer for that, the first answer is we actually don't know. But we have a pretty good guess. So there's a few different theories. And currently, the leading theory was actually presented in 1977. Now, I would like to note that this was before black holes had actually been formally identified in observations. And so if you read the paper at the end, it's quite funny because they start talking about how you might expect to see jets from black holes, but then they have to mention that black holes might not even be real. So it's quite entertaining. But times have changed since then. We see lots of black holes now, as we know. But yeah, so this Blandford, I don't actually know how to say it, Blandford-Zanuck? Does anyone know? Yeah, Zanuck process. So basically, a black hole that is spinning actually kind of, what's the word? It warps space-time itself. So it can actually kind of spin up, like tangle space-time a little bit like this. And we call this process frame dragging. And so yeah, this is an excerpt from the paper. And it says, when a rotating black hole is threaded by magnetic field lines, so if there's a magnetic field that exists around the black hole, like we know in the medium of galaxies, there are magnetic fields, supported by external currents flowing in an equatorial disk, so if there's an accretion disk present, an electrical potential difference will be induced. If the field strength is large enough, the vacuum is unstable to a cascade production of electron-positron pairs, and a surrounding force-free magnetosphere will be established. Under these circumstances, it is demonstrated that energy and angular momentum will be extracted electromagnetically. And so that last sentence kind of is what we would expect to see is a jet. And so you can kind of think of this, if we have a black hole that is tangling up space-time because it's spinning, and you have an accretion disk, you have magnetic field lines. Here you can see if there's a field line, as the black hole spins, it can actually kind of twist up those magnetic field lines, and you end up with a very tangled magnetic field. Now, if you have gas going through around near that magnetic field, particles or like things from that gas can actually get caught up in those magnetic fields and shot out at quite high velocities. And so this is kind of a very basic explanation of the physics behind a jet. So hopefully that kind of helps a little bit, but I think this diagram is also a bit more helpful. So you can see you have the magnetic field lines in red. You might have an accretion disk, that's in blue. You have the black hole that is spinning, and because the black hole is spinning and you have this frame dragging process, it tangles the magnetic field lines, and it will pull gas up into those magnetic field lines, and that's what powers those jets that we see. So, so black holes at all scales grow via accretion. So I've talked about supermassive black holes, AGN. They're growing via accretion at a much higher rate than these stellar mass black holes, which are taking gas from a regular star. But the process of accretion is very messy. And as the material forms a disk, a lot of matter can be blown away, producing outflows. And then on top of that, as the magnetic field lines kind of twist together, you can have these jets released as well. So we actually like to say that there are kind of two types of outflows that we see in these accreting black hole systems. So we have these relativistic or quasi-relativistic jets that are launched from the magnetic field lines and things. But we also have these we call accretion-induced winds. And so the accretion process is quite inefficient. You can actually have matter just being blown off as the disk is rotating and circularizing and things like that. And so in tidal disruption events in particular, this, because it's, the star comes in, it gets stretched, it gets destroyed, collides with itself, that collision drives some matter out and will actually unbind it from the gravitational potential of the black hole. And that will keep happening, and so you can actually have these lower level, slowly moving spherical outflows, as well as these really powerful, highly magnetized jets from these systems. So, okay, that's a bit of an explanation, that's a bit of the background, the theory behind what we observe and how we observe it. Yes, you have a question?
So you can break magnetic field lines, right? And then you can give energy to the medium around it.
So how do you mean?
So I think in the sun, when they have the winds, the wind from the sun, and some of it's caused by the breaking of or joining of magnetic field lines.
Yeah, so like the solar flares and things that they see. Yeah, I think, yeah, that's definitely one process that can release gas from the gravitational pull. That's one way to accelerate it and get it to leave, definitely, yes.
Can it go out radially from the dust cloud?
In a disk?
Yeah.
Yeah, it can go in any direction. Yeah, that's why we kind of end up seeing these spherical, or we say that they're spherical winds, because it kind of is random directions that it will go in. Okay, so yeah, another question?
I had one question. Do these jets, as the accretion is happening and the disk is growing, do these jets wax and wane? They stop after some time and then they start again. Does that something like that happen?
Yes, yeah. So as you saw, like there were kind of knots in the jet in the observations that we had. So the material is not kind of like, it's not a uniform density of stuff in the jet. It can be quite clumpy as well. And jets do switch on and off. So like in these accreting X-ray binary systems, we tend to see jets in a certain accretion state when the accretion rate is quite high. And there's a lot of like high energy X-ray emission being seen. And then if it kind of drops a bit, we see it switch off. So it's very dependent on the actual environment of the accretion disk and how much things are moving in the radiation and things that's present. So yeah, we do see them switch on and off. In tidal disruption events, because it's a very limited supply of gas, it's just one star. We tend to, if we see a jet, we've seen a jet in 4 events. If we see a jet, it kind of lasts a certain amount of time, and then we haven't seen it restart again in those systems yet, at least. Yeah?
What kind of patterns do you see in the outflow?
What kind of patterns?
Yeah. What do you notice? I mean, what are some things like definitely something happened here because this is what we have?
Yeah, so I'm going to go through in a little bit the way that we observe these things and how we watch them evolve. But usually we see an evolving radio spectrum. And I'm going to talk through about the physics of that and how we are then able to constrain the source size and how we know that it's growing. But yeah, we can kind of infer that it's an outflow if we see the emitting region growing in a way that would be consistent with an outflow. Okay, one more question and then we'll go back to the...
Maybe you're going to cover this, but some of the differences between stellar mass black hole jets and supermassive black hole jets, and then it sounds like we have an idea of how the jets form, but maybe we don't know for sure.
Yes.
Can the tidal disruption, watching those events, confirm or help us understand better what's happening?
Yeah, no, that's a really, really great point. So in stellar mass X-ray binaries, the jets evolve quite quickly. They turn on and off relatively quickly on human timescales, so we can watch them. But, a stellar mass black hole, we're talking tens of times the mass of our sun, whereas a supermassive black hole is millions or even billions of times the mass of our sun. And so it's a very different environment and a different process. And that's one of the reasons that we're really interested in watching tidal disruption events, because they give us one of the only ways that we can actually watch the jet launching and switching on in supermassive black holes, because it's very difficult for AGN, they last millions of years. We're pretty unlikely to watch one suddenly switch on in, the 50 or 100 years that we've been observing. So yeah, that's why we're particularly interested in radio emission from tidal disruption events, because they give us a rare opportunity to watch the launching of a jet from a supermassive black hole in real time. Okay, so how do we observe these things? Now, I'm sure as physics teachers, you're all very familiar with the electromagnetic spectrum, I hope. And so I just wanted to point out that we're talking about radio emission, so the lowest energy light. form of light in the electromagnetic spectrum. And so what does the universe actually look like in radio light? Now, I wanted to show you this because I think this is a really cool tool. You can even play around with it in a classroom, perhaps. So you just have to Google gleamoscope, and it will come up. Feel free to Google now if you like. Whoops, let's not make it smaller. I have to show you. Okay, so this is what will come up. It's a website. Again, we've seen this many times today. This is our galaxy in optical light. But the beauty of this website is that you can actually look at the galaxy in lots of different lights. So this is high energy. We're looking at gamma rays and X-rays. As we go down, we're looking at visible, far infrared, microwave, and here we are in radio. So this is what our galaxy looks like and what space looks like in radio light. Now, the one thing I love to point out about this in particular, if you look at all these backgrounds, so I mean, obviously the galactic plane, gorgeous, great, but what I'm interested in is the things in the background, the things that are off the galactic plane. Because in optical light, pretty much every speck that you see in the image in optical light is a star. However, in the radio, pretty much every speck that you see in the background here is an entire galaxy. I like that response, great. It's impressive, right? Yeah, so because we're looking at very different emission mechanisms to optical in the radio light can travel a lot further because we have much longer wavelengths, so it's less likely to be interrupted on its way to us. We can look really far away, and there are a lot of active galaxies out there. So pretty much every single little speck in the background here is an active galactic nuclei, a supermassive black hole driving one of these powerful outflows. And the reason they don't all look like these gorgeous resolved jets like the one up here, this is actually Sen A, which I showed you earlier, is because they're so far away. Yeah, so this is what our galaxy looks like in radio light. And so we're able to kind of probe a very different part of the universe by looking at things in radio. So yeah, I really like this, this demonstration of our Milky Way galaxy. Okay, let's get back to the slides. So, radio observations. So yeah, but how do we actually, take observations in the radio sky? So we use telescopes that are on the ground. We're lucky. So if you want to be an X-ray astronomer, X-rays don't pass through the Earth's atmosphere, so you have to put a telescope in space to observe X-rays, which may be good, may be bad, I don't know. It means you don't have to deal with the atmosphere, but it also is much more difficult to get an X-ray instrument on. But radio telescopes we observe here on Earth, and we have radio telescopes dotted around the entire planet. Here are a few. I think this one is actually my favorite. You'll be glad to know it's in the US. So this is a very large array. It has 27 individual dishes, and it can observe radio frequencies from about 0.6, but no one really uses that band, so 1, up to about 30 odd gigahertz. And so this is radio frequencies. I also would like to point out ATCA, my second favorite one. This is the Australia Telescope Compact Array. Now, it only has 6 dishes. And so we have to stare at things a lot longer with ATCA to get the same sensitivity than the VLA, because the VLA has 27 dishes. I was actually observing with ATCA last night until 3 a.m, so if I'm a little bit sleepy, that's why. And then we also have Meerkat. It's another great telescope. This is in South Africa. Meerkat is actually a precursor for the Square Kilometre Array. If you haven't heard about the Square Kilometre Array, we're currently building in Australia and in South Africa the world's biggest and best radio telescope. And this is, we started construction this year. I say we, like I'm building it, I'm not building it. It started construction earlier this year, and it will revolutionize the way that we see the radio sky. So it's very exciting. It's a huge endeavor. I think there's 12 countries involved. It's an intergovernmental organization to get this radio telescope to look at the universe in radio light. So it's very exciting, and we're hoping to detect many more tidal disruption events with it when it does come online. Yeah?
How does this kind of large array compare with something like the Green Bank telescope?
Yeah, so the single dish telescopes are great for certain things. They're really good at looking at pulsars because they don't necessarily need high resolution. But basically, the more dishes that you have, the better resolution you can get. So you can kind of resolve things in finer detail. And that's why with VLBI, when we get, we don't ever get these three to talk to each other, but when we get multiple telescopes to talk to each other, we get even better resolution. And that's how we were able to resolve those jets from that stellar mass black hole binary. Okay, so yeah, we observe things in radio, but what actually is the radio emission that we're seeing? So most of the time, radio emission, I say most of the time, is driven by synchrotron emission. And so synchrotron emission is a very fundamental physical concept. Basically, in this case, this is synchrotron emission from a jet from a tidal disruption event. That's why I put it on this slide. But basically, you have this jet kind of moving at very fast speeds, so relativistic speeds sometimes. And it's not just moving into a vacuum. In space, there's kind of gas always around, especially in the center of a galaxy. There's a fair bit of gas around usually. And so as that jet moves out, it will impact that surrounding environment. Electrons will accelerate around the magnetic field lines because the magnetic field lines will compress with the shock, because it creates quite a shock with that gas. And they will start producing synchrotron emission. Now, there are two types of synchrotron emission that we can observe in these jets. So we can see synchrotron emission from the shock, we call it the external shock. So from that jet impacting the circumnuclear medium, we say, circumstellar medium, the gas that's in the galaxy. But in some jets, they can be quite energetic, moving very fast. You can actually have internal shocks that also drive synchrotron emission. So you can have internal shocks or external shocks. But most of the observations that I'm going to show you are from these external shocks, we think. Yeah, so synchrotron emission, electrons in the shock, they're accelerated into a power law distribution. So you have many electrons, they're all accelerating around magnetic field lines and emitting at a specific frequency or energy. And they'll have slightly different frequencies or energies that they're emitting. But they will kind of all, so a single electron will emit, this is frequency against flux, brightness. A single electron will have a distribution of energy that it emits. And then as you add up all of the electrons emitting together, you end up observing a single power law. And the peak of that power law, the peak frequency or peak energy, actually tells us a lot about the emitting region, or the region that is emitting the synchrotron emission. And the key thing, at least with tidal disruption events, that it tells us is it can give us a good constraint on the size of the radio emitting region. So synchrotron emission is responsible for many radio emitting sources. Most of the radio emission that I showed you on the Gleamer scope is synchrotron emission, including gamma ray bursts, supernovas, AGN, as well as outflows from TDEs. So this is very complicated. I'm not going to go into a lot of detail, but basically we expect a power law. So the number density goes with a power law. And so these are the different types of spectra that we can observe. So here we've got frequency against flux or brightness, depending on the kind of regime that the synchrotron emitting source is in. So if it's like cooling, or if there's self-absorption or free absorption, all sorts of different kind of how optically thick or thin the gas is that we're looking at. So yeah, this is kind of, there's a lot of maths and physics that you can do to derive this, but I'm not going to do that today. But basically we see these peaked synchrotron spectra. And so the question is, if we're observing outflows from TDEs, we expect to see synchrotron emission because the center of a galaxy is a very dense environment. We have material ejected during the disruption. Actually, about half of the star will be unbound. So about half the star will be accreted by the black hole. The other half will be unbound and potentially could produce this synchrotron emission. So the question is, do we observe these peaked synchrotron spectra in TDEs? So to do that, we need to take observations of these. This is a photo that I took myself with ATCA, my second favorite radio telescope. And this is a galaxy 1.4 billion light years away. And we saw it do an optical flare, like you've seen earlier from Decker's talk. And we also saw it do an X-ray flare, this galaxy. And so we thought there was a pretty good chance that we might catch some synchrotron emission in the radio. And we did. This source didn't used to be there, and now it's there. You can see it's just a point source. It's a single point. It's very, very far away. But we're able to look and see, and we've done this for many TDEs now. Kate has very much helped this as well. And so we've seen synchrotron emission that we interpret as from an outflow from a tidal disruption event. And so what have we seen? Well, these are some of the spectra that we've seen. So this is frequency on the x-axis, flux or brightness on the y-axis, and this is two individual tidal disruption events. So this one is Assassin 14Li, which I think you saw some observations of earlier at a different frequency. This is actually from Kate's paper. And this is a different TDE called AT2019EZH. They never have fun names, don't ask. But basically what you can see, so this is the expected synchrotron, this is what you would expect to see from synchrotron emission, and this is what we saw. So we saw these peaked synchrotron spectra. And the most interesting thing is that these spectra, so the colors were taken at different times, and these observations were like spaced, there were months between each of the observations. So we watched these evolve. And if we watch these evolve, and we're measuring the peak of the synchrotron emission, and that gives us an idea of the size of the radio emitting region, we can then constrain how the outflow is growing. We can get its velocity, we can get its radius over time. So that gives us a constraint on the velocity. And really interestingly, for these two events, these were not moving at relativistic speeds. And so we actually interpret these not as relativistic jets, so we don't think that they were jetted. We think this is more a spherical outflow produced from the collision shocks or accretion-induced wind or something like that, because these are very slow outflows and not evolving particularly quickly. So yeah, that's kind of one of the things that we can do by observing radio emission from TDEs. So yeah, recent observations of jets and outflows from TDEs. So just to kind of reiterate the point, when the star is destroyed, all the X-ray and optical emission comes from near the black hole and the bound stellar debris. But what we're looking at now is the unbound stellar debris. So about half of the star can be ejected. Occasionally we can get these jets, but we think that you have to be pretty lucky to see a jet because they're quite narrow and they're not pretty unlikely to be pointed towards us when there's 360 degrees that they could be pointed towards. Or we actually think maybe that some events might not even produce jets because it does depend on the magnetic field and the accretion rate and all those sorts of things as well. So we're still not sure about that. So yeah, this is just to kind of give an indication of how slowly they evolve in the radio. The optical flares happen relatively quickly, over a month or two. So this is a light curve again. We've got time on the x-axis, brightness on the y-axis in each of the three panels, and again, time and brightness. And so you can see this evolves over 100 odd days. This one we actually saw an infrared flare, which is quite interesting. But the radio flare happens quite a bit later, and it lasts a lot longer. So it's still going. This has been going for about 3 years now, and I'm still looking at it, and it's still decaying. So the radio emission kind of, as that outflow, it'll be shocking the gas that it's moving into. It actually will start eventually to decelerate and fade away, we think. That's what we're observing. Yeah, and similar with this one, we detected it in the radio about here, and we've been watching it evolve for quite some time. So how many TDEs have we actually seen these outflows from? I want to point out that this is actually a really new field. So the first radio detected TDE was in 2011, and it was a jetted event. We got very lucky. We saw that one. But these non-jetted events, the first one wasn't detected until 2014, and it was published in 2016. And we didn't know initially that we would see radio emission that weren't from jets. We thought these things are so distant, they're really distant galaxies, the kind of accretion-induced wind outflows are probably a bit too faint for us to see, and so we didn't know to look for these slower moving outflows that might not be jets. And so between 5 to 10 years ago, this is, you can't see the axes. Anyway, I'll just tell you, this is time and brightness in the radio. This is how many TDEs we had detected in the radio. So not that long ago, this is all that we knew. But now, thanks to dedicated radio follow-up programs, this is what it looks like. So we've observed a lot more, and we've detected many more events. Again, this is time and brightness. I don't know why it's not showing up. But what's particularly interesting about this plot is that they don't all look the same. Yeah, you might think, you know, given its very standard synchrotron emission, it should be a radio emitting region that's expanding. You might think that they should look pretty similar, but actually there's many different things that go into producing the radio emission that we see. And so the environment can play a huge role, how dense the gas is in the center of the galaxy that the shock is hitting, so then how energetic the shock is in a way, as well as how the star was destroyed, how energetic the collisions were that drove the outflow perhaps. All those sorts of things can go into changing the radio emission that we see. And so it's very difficult to disentangle. And so just to point it out, these are two relativistic TDEs up here. So you can see they are orders of magnitude brighter than the non-relativistic ones. So these are moving at relativistic, well, were moving at relativistic speeds. We think they're consistent with a jet that was produced during the TDE, but the much more common ones are these non-relativistic ones. And these are more consistent with kind of a spherical type outflow that's moving through the central region of the galaxy and producing this synchrotron emission. So we've learned that radio emission is actually pretty common from tidal disruption events. There are still some that don't seem to produce radio emission. We're not too sure why that is, but we're trying to figure it out. But there is a lot of diversity in the population. And just as we come into the last few minutes, I wanted to highlight some of the exciting things that we've discovered. And it's these late time radio flares. So there's a few events where this is, you can't see the axes, but this is more than 1,000 days after the star was destroyed. We're seeing really quickly rising radio emission. And we don't actually have a good explanation for it. The theorists are really debating this quite strongly. And so the best theories are that maybe it was a late launch jet. So maybe it took that long for the accretion disk to form, to kind of get to the point where the magnetic field was strong enough, was tangled enough that a jet could be launched. And so maybe these events were actually seeing jets that were launched 1,000 days after the star was destroyed. Other people think that perhaps this could be new interactions with the supernuclear medium. So in the center of a galaxy, the black hole, it's thought, might clear out a cavity around it, and this would kind of, when it reaches the edge of that cavity, it might hit quite a dense cloud of material, and that could drive a more powerful shock and then cause a rise or a flare in the radio emission. And then other people again say that maybe we are seeing an off-axis jet. So if a relativistic jet is initially off-axis, we won't see it. But as it decelerates, it becomes less collimated, so it starts to laterally expand. And as it kind of starts to expand, eventually it might expand so much that it comes into our viewing angle and we might be able to see it. So these are the theories. We're taking more observations and we're trying to figure these things out, but there's a lot of new and exciting things in this field. Yeah, so I just want to, this is my final thing. So if we look at the spectra of multiple events, so these are the peaked synchrotron spectra, we've got frequency against brightness for many different events, we can then get an idea of how quickly these things are moving and what their velocities are like over time. And to me, my favorite thing that we can do is we can actually track back. So if we're measuring the radius every few months for a few years, we get a good estimate of the velocity, but we can actually track backwards in time and figure out when T0 was, so when the outflow was launched. And that then gives us an idea of what might be producing this outflow. Is it a jet from the disk? Is it a wind from accretion? Or was it launched earlier when the initial collisions were happening of the debris stream? And for these events, this handful here, it seems that the outflow was launched when we first saw the initial optical flare, which would imply that these outflows were launched from the collisions of the debris streams. But there's a bit of uncertainty in this. But then for some of the late flaring ones, so these are the late flaring ones, we have time and radius on the y-axis, the radio emitting region size is not consistent with being launched at early times for some of them. Not all of them, but for some of them. And so that could be indicative that this was a late launched jet. So maybe it took a while for the accretion disk to get to the point where it was able to launch a jet. So black holes at all scales grow via accretion, but the process of accretion is very messy. So black holes are messy eaters. And this often produces bright radio emission in the forms of jets and outflows that we can detect. Outflows can be relativistic narrow jets, or they can be slower spherical type outflows. And the beauty of tidal disruption events is that they allow us to watch the launching of jets and outflows from supermassive black holes in real time, whereas for AGN and the much longer-lived active galactic nuclei, we don't get to watch the launching of the jets from supermassive black holes. And recent radio observations of TDEs have found that black holes may launch jets years after destroying the star, which is particularly interesting. Now, before I finish, I know this is my summary slide, but I did just want to talk about this. So this is something that I show when I go to visit schools. So in Australia, I often go out to speak to schools. I tell them about my career, about what I do. I get them excited about black holes and astronomy and things like that. And the kids always want to know how I got to where I am. And so I show them this story. And I think as physics teachers, I would really like to show you this, because I think there's something that you could take out of this message. So when I was young, I was obsessed with space. I wanted to be an astronaut. This is me. I won a medal for a project I wrote called Living in Space. So I was just obsessed. I wanted to, this is why I was scared of black holes, because I just, I wanted to hear about everything. But then when I went through school, I kind of grew up a bit. I was encouraged to do other things, and I actually didn't do physics in high school. We had no girls in my physics class in high school, and this was not that long ago. And actually, I was really good at maths. I loved maths, but my maths teacher, he told me I wouldn't do maths at university, which my response was, if I'm not going to do maths, then who is? But he was just this very traditional person. He thought I was interested in other things. I mean, I was actually top of his class. Like, it wasn't that I was bad at maths either. He just thought I wasn't interested in it. And that can be quite damaging for some students. I know my sister, for example, she had him as a maths teacher as well. And after he said something similar to her, she didn't do maths. I mean, she went on and got a degree in medicine, but that doesn't decide the point. I think it's a shame that sometimes these experiences that we have in the classroom can really affect what we do and who does certain things. So yeah, I picked up physics in undergrad, and I kind of refound my passion for astronomy and astrophysics. And yeah, I continued on, and I'm now a lecturer at Curtin University in Perth, Australia. But I just think as teachers, I think, if you can take this message and just, think about encouraging people to do physics, because physics is for everyone. Astronomy is cool. Black holes are awesome, and there's so much that we can learn about the universe. So thank you.
All right, thank you very much, Adele. We have lots of questions, so maybe start up here in the front and we'll work back.
Could you talk a little bit about the observing process? Because in some cases for telescopes, I think they're like robotic and you request something, but then you said you were up till 3 p.m. or a.m.
3 a.m., yeah.
Yeah. So just curious how that works.
The majority of radio telescopes nowadays, they employ telescope operators. And so as a researcher, there'll be a group of researchers, we'll put in a proposal. So we'll come up with a science case. We'll say we want these observations for these reasons. This is why it's relevant, cool, exciting, whatever. We put that in. The proposals get assessed by a TAC, so an assessment committee of people who are scientists usually. And they rank the proposals, and then they divvy up the telescope time that way. And these proposal rounds usually are every 6 to 12 months for different instruments. And so once you get the time on the telescope, usually, so for the VLA, for example, and for Meerkat, you then write a schedule file. So they have online portals that help you write the correct schedule file in the format that the instrument wants it. And then you send that to the telescope, and they have an operator that will operate the telescope and take the observations. And then they send us back the raw data, and we reduce the data, calibrate it, image it, and all those sorts of things. But with ATCA, it's a relatively small instrument. It's only 6 dishes. They don't have a whole lot of resources. And so they actually outsource the observing to the scientists. And so I log in remotely. It is still it's mostly self-sufficient. So I log in remotely. I've already created a schedule file. I'm the one that sets the schedule file. I do the calibrations and make sure the weather's okay and make sure the telescope's not complaining about anything. And then I watch it for, last night was 12 hours. As I stare at the same thing. And I was last night observing a tidal disruption event. So it can be different. It's very much dependent on the instrument team, on how the observing happens.
think we have the other microphone back there.
So maybe this is a clarification. When you talked about the frame dragging, you had like it was electron-positron pairs.
Mm-hmm.
But in the synchrotron emission, it said electrons then P plus. Is that protons or positrons?
I think that's protons. So the synchrotron emission is not due to the frame dragging. So it's kind of a separate thing. So the frame dragging is what causes the magnetic fields to twist, which then launch the jets. But the synchrotron emission is a different process in which the particles and stuff inside of the jet, a shock forms, and that shock produces the synchrotron emission. So hopefully that clarifies.
I have a question about what you mean by seeing the jets, because my understanding is that these jets are concentrated beams of relativistic electrons and positrons, and when they slam into stuff, they emit synchrotron radio emissions and some X-rays in all directions, I thought. So what do you see if you're looking down the barrel?
Yeah, so I think it's kind of about the brightness of what we see, and so if it's kind of going like away from us, it kind of would probably, if it was right in front of us, we should be able to detect something, but because it's so far away, it's brightest if it's facing straight at you. So yes, there is some emission. But the most amount of emission we get is when the jet we're looking straight down, at the jet.
So the larger part of those radio photons, the synchrotron, are going with the jet.
Yes. Yeah. Exactly. Yeah.
So I have a question about clarify the mechanics. So you have a galaxy and it's got some rotation, so that's the galactic plane. But then the black hole itself, does it have to be rotating matched up with the galactic plane? And then on top of that, if you have a star that's a TDE, it doesn't necessarily have to come in along the plane, right? It can come in from above or below. And so does the accretion disk form at an angle, or does it then coincide? And then, of course, you've got the magnetic field, right, and the axis of the magnetic field, and then the jet is that lines up with the axis of the magnetic field, or the rotation of the black hole, or the rotation of the galaxy. So as you can see, I'm dazed.
Yeah, I mean, honestly, our scientists have the same questions. The black hole, the star, as you quite rightly said, the stars that produce these stellar disruption events, where the star is entirely disrupted, usually come on quite elliptical orbits, and so they can be like off the plane, or they can be in the plane, or wherever. But the galaxies that we identify tidal disruption events in, we intentionally choose very quiet galaxies that don't really have an active nucleus already, because, I mean, not because tidal disruption events don't happen in active nuclei, but more because it's very hard to disentangle the emission if it happens in an active nucleus. So we look for quiet ones where there's not really, it might have, previously already had an AGN phase, so there's not much gas available, or it's not had its AGN phase yet, and so there's it kind of takes away one of the issues with observing the emission. But you're quite right that the disk can be, from the TDE, could be oriented in any direction to the galactic plane of the galaxy.
Can you get multiple jets if you have multiple stars coming in?
I think the probability of them happening near each other is probably quite low, but yeah, you're better off asking one of the people that simulate the dynamics of the TDE, so Brenner or someone might have a better answer to that.
All right, we've got, I think you had your hand up first, and then we've got a couple more questions over there.
Do you ever combine all your telescopes, like the Event Horizon telescope, to do your observations?
Yeah, so we don't use the Event Horizon telescope, but we have got some VLBI programs. So there are some Northern Hemisphere networks of radio telescopes that will work together, and we have looked at a handful of these events in VLBI. So especially the relativistic ones, that we have the biggest chance of resolving anything because they're moving the fastest. But for the slower moving outflows, we've looked at one of the ones I showed. We've been trying to look at it every year for the past 4 years to see if we detect anything, but it's so far away and it's not really expanding very quickly, so it's still just a point source even at the highest resolution that we can look at it with. But we're trying.
Yeah, we had 2 questions over there. I think we have time briefly, maybe.
My question is that the accelerator from nature, for us now, we have man-made accelerators like particle accelerators that we learn a lot from what comes out. Are we using that knowledge that we have for this natural type accelerator that's coming out so that we can understand more of what's going on?
Yeah, definitely. I think we're trying. I mean, yeah, synchrotron emission is something that you can you can do in a lab. And so I think we have learned a lot about how we might expect the emission to look and the power, like the distribution of the things from those experiments. Something completely unrelated, but something I worked on during my PhD was I was working on these things called X-ray bursts. Now, these are huge explosions that occur on the surface of accreting neutron stars. So not black holes, but very similar to the black hole X-ray binaries, but instead of a black hole, it's a neutron star. And because it's a very dense environment, it's a very hot environment, and you have gas, regular gas, accreting onto the surface of a neutron star, you can actually get these thermonuclear runaways, and you have all of these nuclear reactions occurring they're quite interesting and difficult to replicate here on Earth. So during my PhD, I was working with a group at MSU in the States, and they were actually nuclear physicists trying to observe nuclear reactions in their lab. And many of the nuclear reactions that they were trying to observe are ones that happened in these explosions that I was looking at in space with X-ray instruments. And so we were trying to, help each other as much as we could, see if we could constrain reaction rates and all those sorts of things. So yeah, we do try and work together when we can.
And I think, unfortunately, we're going to have to cut it off there so that we can end on time. So let's thank all of our speakers for the day again. And then I'd also like to thank KITP for having such a wonderful venue and such wonderful staff, bringing all of us scientists here, as well as all of you wonderful educators. I just think it's really great we all get the chance to be here and learn from one another. And I hope you all really enjoyed the program. Don't forget to turn in your surveys, and the shuttle back, if you need it, will be leaving from outside the building. So thank you all so much. Enjoy the rest of your day.